Alright, so welcome to part 2. So now we will focus on, well, the main goal is to show the existence of, let's say, a removable edge in most bricks. There are of course small exceptions, but in fact during the break I was thinking that maybe we can do it slightly in a better way. So let's try to see how we proved or how you observed that there is always a removable class in any brick, right? There is a minimal class, that is clear. In a brick there is a minimal class, well in any matching code graph there is a minimal class, right? Every finite poset has a minimal element. So there is a minimal class, and because bricks are 3 connected, it follows by the previous chapter's result that a minimal class will have cardinality 1 or 2. But then because bricks are 3 connected, a minimal class will be a removable class. Yeah, everybody agrees? So the way we proved the existence of a removable class is by actually focusing on minimal classes. Yeah. So let's do that. Let us consider a matching code graph G. Forget brick, just take any matching code graph G. Matching code graphs are 2 connected except K2. Let me throw away K2. Therefore, each vertex has degree at least 2. Yeah? Let me look at a vertex of degree K, or I don't know, degree D. Let's say V is a vertex of degree little d. Let me just draw a vertex V. This is my vertex of degree 5 in this example, d equal to 5. I don't know parallel edges and all that, I don't know, but there are some 5 edges going out. Each edge, if each of these edges belongs to a minimal class, then we are done, no? If each of these edges belongs to a minimal class, then we have 5 minimal classes. Do you all agree? I am not double counting. I am not over counting. If each of these edges belongs to a minimal class, then we have D equivalence, D minimal classes. Observe this. If each edge in partial of V lies in some minimal class, then I would like to claim then G has, in fact for this argument I did not even have to exclude K2, but anyways fine, K2 is annoying. Then G has at least D Is that a correct statement? Do you all agree? 2 edges cannot belong to the same minimal class. In fact, 2 adjacent edges can never belong to the same equivalence class. You all agree with that? Equivalence class is a matching. May not be perfect, but it is a matching. Yeah? Suppose one of these edges does not belong to minimal class. Supposing these 4 belong to minimal classes, but this last fellow, E, does not belong to a minimal class. Then can you still give me 5 minimal classes? Supposing first 4 edges, E1 to E4. Supposing E1 to E4 belong to minimal classes, but E5 does not belong to a minimal class. Can you still give me 5 minimal classes? You can, right? Is that right? E1 to E4 belong to minimal classes, but E5 doesn't. Then I claim that there are still 5 minimal classes. Think about it. You have to think hard about posets. Does this lead you to a concept? Now I want you to generalize this. Convince me that I can throw away this assumption. Convince me that, or convince yourself rather, that you can throw away this hypothesis. The hypothesis is actually not necessary. Convince yourself that the graph has at least 5 minimal classes. And convince yourself that you are not double counting any of them. Yeah? Okay, so see if you can write down a formal argument. Convincing is one thing. Now see if you can write down a formal argument. How do you formally write down that the graph in this case has at least 5 minimal classes? Okay, I'll come and talk to you. Right, so I'll define minimal classes again, just as a reminder. Right, so the equivalence classes are clear, right? So dependence itself is not an equivalence relation, but mutual dependence is an equivalence relation, right? Two edges are mutually dependent if every perfect matching either contains neither of them or both of them. That's one way to think about it. This is an equivalence relation, and this equivalence relation gives us the so-called equivalence classes, which we unfortunately call equivalence classes, right? But now on these equivalence classes, that are defined by mutual dependence, you can now define dependence on them. One class depends on another class. Let's say Q1 depends on class Q2. If some edge in Q1 depends on some edge in Q2, which is equivalent to saying that every edge in Q1 depends on every edge in Q2. Right? So now observe that what we now have is a relation that is reflexive and transitive and actually anti-symmetric on the set of equivalence classes. Right? If Q1 depends on Q2, then Q2 in fact cannot depend on Q1 unless Q1 is equal to Q2. And this is a poset. This is a partial order on the set of equivalence classes. Right? And now because it is a poset, we can use some poset terminology. In particular, we can talk about minimal elements of a poset. Every finite poset has a minimal element. So the minimal elements of a poset are those elements on which nobody else can depend as per our dependence relation. So if you think of drawing your poset as a directed acyclic graph, almost the same as the Hasse diagram of a poset, not very different really, then these are exactly the sources of your directed acyclic graph or of the Hasse diagram. Right? So the source elements are exactly the minimal elements and vice versa. Yeah. Okay, so now think about it. So the point is, I want to get rid of this hypothesis completely. I don't want to have any hypothesis. I want to just look at a vertex of degree d, and I want to claim that there are at least d minimal classes in this graph. And so the point is, if the edge belongs to the algorithmic way of looking at it, is if the edge belongs to a minimal class, good, be happy. If it does not belong to a minimal class, then there is some fellow who depends on that class. There is another class that depends on this class, because this belongs to some class, right? Every edge belongs to some class, some some equivalence class. So if E1 belongs to Q1, E2 belongs to Q2, E3 belongs to Q3, and so on. These are all distinct equivalence classes. That you all agree? Q1, Q2, Q3, Q4, Q5 are all distinct equivalence classes. They may not be minimal. If all of them are minimal, we are done. If this fellow is not minimal, then some class depends on it. So you go to that fellow, Q1 prime. If this is minimal, then you are done. Q1 prime, Q2, Q3, Q4, Q5, you are done. If this fellow is not minimal, then that's because, so I should put the arrow in the other row. Somebody else, Q1 double prime, depends on this fellow. You keep doing this. Eventually you will reach a Q1 star that is actually minimal, and there is a dependence from Q1 star to this Q1, which is the one containing E1. Likewise, you will get a Q2 star for Q2 in case Q2 was not already minimal, otherwise the Q2 could be equal to Q2 star, right? So you will get one fellow here like this, and so on. Now observe that these star fellows are actually distinct from each other. Because if Q1 star is equal to Q2 star, then take a perfect matching containing Q1 star, which is equal to Q2 star, and observe that it contains E1 and E2, which contradicts the definition of a perfect matching, right? So therefore, these star fellows you will get are indeed minimal classes, and you got 5 minimal classes that are pairwise distinct. Of course, I don't like this, as you can imagine, right? This is very verbose. So we will introduce a terminology. We will talk about a minimal class induced by any edge. For every edge of a matching code graph, one may define a minimal class induced by that edge. It is some minimal class that depends on that edge. You can also talk about dependence between classes and edges, right? Is that okay? We can also talk about dependence between a class and an edge. Is that fine? Okay, we don't need to define it, right? So, for any edge of a matching code graph, there is a minimal class that depends on that edge. That could be the minimal class containing that edge itself. That could be the equivalence class containing that edge itself. Right? So this is what we will define. Observe that this is not, I cannot say the, I have to say minimal class induced by an edge. This actually is defined in chapter 8, but I did not feel comfortable defining it there. A minimal class induced by an edge E of a matching covered graph G. What is this? This is any minimal class Q of G such that Q depends on E in G. Every perfect matching containing Q must also contain E. Yeah? And observe that it is possible that Q itself contains E. If E belongs to a minimal class, well then it is the unique minimal class. In that case it is actually unique. Right? In that case there is no other minimal class that can depend on E except the class that contains E. Yeah.
there will be d minimal classes which are not depending on each other.
Right, exactly. So we actually proved something stronger. Here. Not only did we prove that there are d minimal classes, we proved that these d minimal classes have a very nice property. They are what Carvalho-Lucchesi-Murthy call mutually exclusive. Two equivalence classes are mutually exclusive, Q1 and Q2. If there is no perfect matching that can contain both Q1 and Q2, that contains Q1 union Q2. Right? Let's also define that. We actually proved a more stronger statement. Two equivalence classes Q1 and Q2 of a matching covered graph G are mutually exclusive and therefore distinct from each other if there is no perfect matching that contains the union. If there does not exist any perfect matching M such that Q1 union Q2 is a subset of M. In fact, what we proved is the graph G has at least d minimal classes that are pairwise mutually exclusive and therefore pairwise distinct. Yeah. All right. So therefore, every brick has at least three removable classes. It has at least three minimal classes, but in the brick a minimal class is a removable class. Therefore, a corollary is every brick. In fact, we can write in terms of delta. This I think is 9.6. Every brick has at least delta max degree removable classes, and since bricks are 3 connected, this implies at least 3. Much stronger. Right? This is the power of dependence. A lot of these things, earlier proofs were actually pretty, non-trivial. In fact, I think people did not know this. They just knew that there is one removable class. And even that, I think the proofs were not as straightforward as some of the ones that we have covered. But now if you go through dependence, you directly get delta removable classes. You don't have to prove anything, you just have to observe things. And there's no proof here. Right? Okay, so you have at least delta removable classes. What we are really interested in is removable edges. Let me see if I can motivate this in a certain way. So, hopefully you are convinced by this point in the course that for a lot of things about matching covered graphs, you just need to prove it for bricks and braces, and generally bricks are the ones that create troubles, right? So you want to prove things for bricks. If you solve the problem for bricks, then you actually solve it for all matching covered graphs. Some of you have already seen this in your research, right? So what you would like is an induction tool for bricks, right? That's generally how we prove things. We first reduce the problem to bricks and braces, or in general graph theory, we reduce the problem to, let's say, 3 connected graphs. That's how we prove Krotowski or Wagner's theorem in SGT. And then you want to prove the theorem for 3 connected graphs now that you've reduced it. So you need induction tools for 3 connected graphs. And the standard tools for 3 connected are Tut's-Wheel theorem and Thomasson's lemma, right? In the same way, we would like induction tools for bricks and braces. Braces are kind of nice. You delete, first of all, in a brace, we have already discussed, in a brace of order 6 or more, every edge is removable. You delete an edge, well, you may not have a brace, but you at least have a bipartite matching covered graph. If you work hard enough, you can probably recover a brace. So that is one part of the story. In bricks, things are actually much harder. Because in the case of a brick, I have a brick. If I delete a removable doubleton, well, then there is no coming back, because now I have a bipartite matching covered graph. Right? We already discussed. Brick minus removable doubleton is a bipartite matching covered graph. How will you recover a brick from a bipartite matching covered graph? Something that is actually useful to the original brick. That doesn't seem so easy, right? So in some sense, for bricks, what you would like to do is not delete removable doubletons, but delete removable edges. Now the problem is, if I have an edge E that is removable, I know that B of G minus E is at least B of G, which is equal to 1. If it is equality, then in some sense we are good. Then I have a matching covered graph with only one brick. It is not a brick itself, but it has only one brick. These are called near bricks. So we are near to a brick, as the word suggests, right? And maybe we can shave off those bipartite creatures and actually get a brick out of it, right? But what if the B of G minus E is strictly greater than B of G, therefore strictly greater than 1, which is what happens in Peterson. You delete an edge from the Peterson graph, you get a matching covered graph with exactly 2 bricks. That's bad news. So this is what people wanted to prove. They wanted to prove the existence of what is called a B invariant edge. A B invariant edge is a removable edge whose deletion does not change the number of bricks. In the Peterson graph, there are no B invariant edges. Every edge is removable but not B invariant. But let's look at another example. This is the bicon, also called H8 in Lucchesi Mutti. This fellow has only one removable edge, and that removable edge happens to be B invariant. That edge is this edge. Observe that if you delete this edge, you get 2 degree 2 vertices. The degree 2 vertex and its neighbors, they comprise a shore of a tight cut. This degree 2 vertex and its 2 neighbors comprise a shore of a tight cut. I'm looking at G minus E. And degree 2 vertex looks like this, right? One contraction is C4 with multiple edges. That is a brace. So I will throw it away. It is the other contraction that has all the bricks, if any. Right? So what I can do is I can delete this edge and I can replace this degree 2 vertex and its 2 neighbors by a single vertex. That is just a tight cut contraction. I can do the same thing here. What is the graph you get? K4 with a multiple edge. What you will get is K4 with a multiple edge. These 2 edges are your multiple edges. When you delete the edge and then you bicontract, this operation, by the way, is called bicontraction of degree 2 vertex. It is a special type of tight cut contraction. So if you delete the edge E and you bicontract U and then you bicontract V, what you will get is this graph. Right? That is a brick. So we started with a brick, we got a smaller brick. So that is why it would be nice if we can prove the existence of a B invariant edge. That is done in part 2 of the book. First thing is, can we prove the existence of a removable edge? Right? What we have right now is delta removable classes. These could be singletons or doubletons. It would be nice if we can say that there is one removable edge amongst these delta. That would be great. Turns out that is true. We will prove. every brick except K4 and prism has a removable edge. We know that there are 3 removable classes, at least 3. Observe that K4 and prism have exactly 3 removable classes, and each of them is a doubleton. K4 is very clear. Every perfect matching of K4 on deletion gives you C4. That is a removable doubleton. In the case of a prism, observe that every edge of a triangle, there is a natural companion in the other side. You delete those 2, you get a bipartite matching graph. You get a ladder on 6 vertices. So therefore there are 3 removable doubletons. And the middle 3 edges are actually not removable. The triangle edges actually depend on them. Yeah. So this is what we'll prove. Every brick except K4 and prism has a removable edge. And the way we will prove this is using Carvalho-Lucchesi-Murthy's idea, which is related to mutually exclusive. So what's the problem? I can apply this result. I will actually get delta removable classes, and in fact, as we discussed earlier, they will be pairwise mutually exclusive. So the problem is, if I get all the delta are removable doubletons, that's the problem. If any of them is a singleton, I'm done. So the question is, can I actually have delta pairwise mutually exclusive removable doubletons in a brick? Yes, K4 and prism. Turns out only. Nobody else. That is what we'll prove. What we'll prove is the following. We will prove that if you have a brick G and you have a brick that has 3 pairwise mutually exclusive removable doubletons, then G is either K4 or the prism. This is what we prove. If we prove this, then this is a corollary. Yeah. Okay, so this is what is coming up. So there are 3 things coming up. And before I repeat those 3 things, let me also mention that for bricks that are not near bipartite, we are actually done. There's nothing to prove. If a brick is not near bipartite, which means it does not have a removable doubleton, well then you actually have delta removable edges, right? So that case is done. The interesting case is actually the near bipartite bricks in some sense. So there are multiple ways to prove this point. This is one way to prove it. This is how Carvalho-Lucchesi-Murthy proved it in 1999, and this is also the way they prove it in the book. So I will just follow that. But there are various ways to get to this final desired result, right? Anyway, so we will prove the result. This will imply this, and the other 2 things we will prove is the monotonicity results, right? If you delete a removable doubleton, B and B plus P both go down by exactly 1. Whereas if you delete a removable edge, then both of the quantities either remain the same or they may increase. And in fact, you cannot control the increase. You can actually construct a brick, not only a brick, you can actually construct a cubic brick if you like. For any arbitrary integer k, positive integer k you like, you can construct a cubic brick such that it has a removable edge so that B of G minus E is equal to k. So there is really no hope to do something unless you have stronger properties, but then you are looking at a special class of bricks, you are not proving for all bricks. Yeah. So anyway, so these are the 3 things that are coming up in this chapter, and try proving the monotonicity for edges on your own. It's really not that difficult. See if you can prove that 9.8 yourself. just use non-trivial tight cuts as your induction tool. 9.9, the proof is more difficult, at least based on my look at Lucchesi-Murthy. I used to think that 9.8 is also difficult, but well, back then I was a PhD student. Now I feel it's quite easy, but also because we have already covered a lot of stuff, so that makes it easy, right? But yeah, anyway, so we'll prove 9.8, 9.9, and we will prove this fellow, 3 pairwise mutually exclusive removable doubletons. I just need to figure out what is the order in which you're going to prove it. I don't know yet. We'll see. Yeah. Okay, that's all for today. We can conclude here, and we will meet again on Wednesday. So the plan is to have all the lectures until I leave for Gujarat. That means 4 more lectures. And then once I come back from Gujarat, we will see what to do. Because I would like to finish the whole part 1 of the book. It would be kind of very sad if we finish everything up to chapter 10 and not the last 2 chapters. So we may do some more lectures in the summer to finish the entire part. Also for all of you, to not see the year decomposition theory fully will also be kind of sad. So let's just try to finish the whole part 1. And I think part 2 and part 3, I don't know when it will happen. Hopefully someday. Yeah. Okay, thank you. See you on Wednesday. Are there any questions or concerns? No? All good? Okay, thank you.